Welcome to a series of 6 presentations commemorating the publication of the first edition of the Ontario Highway Bridge Design Code in 1979. These presentations were made first at a special session at the 2024 Canadian Society for Civil Engineering Annual Conference in Niagara Falls. That was the 45th anniversary of the first edition's publication on June the 6th. They were recorded at a Ministry of Transportation webinar on May 12th, 2025.
It's really my honor to introduce this special session and these guest speakers today for something that's very important and historic topic. It's difficult for me to express my appreciation for these engineers and the work that they did and the way that they advanced bridge engineering during their time. You know, in 1975, Roger Dorton, who was a manager of bridge office at that particular time, wrote a proposal to write a code. It would be only metric. It would be a limit states design code. It would be the first such comprehensive limit states design code for bridge design worldwide. In fact, it was a major revolution. People took note internationally, and it actually spurred development of other codes, including AASHTO LRFD, which came out some 15 years after we released this first code in Ontario. So to give you an idea of the scale of this code development, you had 80 members, half of MTO was involved, and at a time when there really wasn't any kind of Canadian standard for bridge design. The Canadian standard at the time was quite out of date. The people presenting here are a bit like my idols and superstars. I never even really thought that I would meet them. And then, you know, I came to MTO and I started speaking with some of them, and over the years have learned a few things, and it's just incredible that they're still with us and still sharp and going to explain what they accomplished some 45 years ago, or actually almost 50 years ago when the whole thing started. So I'm really humbled and privileged to introduce the speakers today. I'll pass it on to Khaled.
Our first speaker is Khaled Bakhtash, who is an Area Manager Construction in the Capital Program Delivery Branch at the Ontario Ministry of Transportation in London, Ontario. Khaled earned a Master of Engineering in 2020 and a Bachelor of Engineering Science in 2017 from the University of Western Ontario. He served as the liaison between the CSCE National History Committee and the 2024 Annual Conference Local Organizing Committee, and played a major role in coordinating the Ontario Highway Bridge Design Code First Edition Commemoration Ceremony. He will be speaking on commemorating the publication of the 1979 Ontario Highway Bridge Design Code. Good morning, everyone. I hope everyone can see my screen. Like Chris said, it is also my privilege to be part of this session and to welcome our speakers today. What we've done here is we've tried to recreate a session that was hosted at last year's Canadian Society for Civil Engineering Annual Conference in Niagara Falls. We commemorated the 45th year of the publication of the Ontario Highway Bridge Design Code. I will provide a brief overview of what to expect in the next 2 hours, but I want to extend my gratitude and thank you to Dr. Mike Bartlett and the organizing committee at the conference, as well as some other volunteers that helped us in the background put together the session. We wrote 6 papers that were submitted to the conference that were accepted and then formed the basis of this presentation. So some of the branding and formatting that you see on the slides are from that special session that we presented, and we tried not to change anything from that session. Our intent, again, is to bring back these pioneers of bridge design code that led to advancements in design codes elsewhere around the world. So without further ado, I will get started. There are 6 pieces to this presentation. I'll start with providing an overview of the session, a little bit background on the rationale for creating this new bridge code. Then we'll review the development of the new code and its implementation through 3 different editions. And then finally, we'll identify some of the major players, and then I'll make some closing remarks before passing it on to our actual guests who are here to present their sessions. In today's commemorative session, we will feature this introduction slides that I'm going through, as well as 5 companion presentations. Akhilesh Agarwal will talk about the development of the new traffic load models, and Bedar will describe the new bridge and analysis provisions. Dr. Bartlett will talk about The Conestoga River Bridge, which was the first bridge that was designed using this new standard. We'll go back to Dr. Bedar Bhatt, and he's going to talk a bit about the development of the new provisions for soil steel structures in the code. And then Andy Nowak will detail the calibration of the new limit states design provision that was incorporated into the code. Any discussion of the code of the Ontario Highway Bridge Design Code should start with a brief description of its key proponents. Paul Chogley and Roger Dorton, both were Ontario Ministry of Transportation and Communication, which was the name of the ministry at the time, engineers, who served as the chair and vice chair, respectively, of the Code Control Committee. We were unable to find a photograph of Paul Chogley. He came to Canada during the Hungarian uprising against the Soviet occupation in 1956 and led the MTC Structures Research Group until 1979. He eventually joined the Florida Department of Transportation and played a major role in writing AASHTO's first limit states design code that was published in 1994. Dr. Roger A. Dorton earned his bachelor and PhD degrees from the University of Nottingham. He immigrated to Canada in 1954, meeting his future wife on the transatlantic crossing. He joined P.L. Prattley's firm in Montreal, redesigning the steel cantilevers of the Champlain Bridge in Montreal, and after Prattley's death, designed the Murray-McCabe Bridge across the Narrows at Halifax. He joined Ministry's Engineering Research and Development branch in 1972 and was promoted in 1976 to be manager of the MTO Bridge Office, where he headed the development of the 3 editions of the Ontario Highway Bridge Design Code. In 1993, he returned to private consulting as the head of the Ontario office of Buckland and Taylor Limited. Dr. Dorton's autobiography spanning the years is the source of a lot of what's being presented in this paper. Dr. Dorton co-authored a paper about the Conestoga River Bridge that won CSCE's Gazowski Medal in 1977. He won CSCE's A.B. Sanderson Award for contributions to structural engineering in 1988, and the Gordon Poos Award for contributions to Canadian civil engineering history in 2016. He's also received honorary degrees from Waterloo and Queen Universities in 1989, and he was made a member of the Order of Canada in 2004. As Chris kind of alluded earlier at the beginning, Dr. Dorton identifies in the book a perfect storm of circumstances in the mid-1970s that justified the development of a new bridge code for Ontario. There were shortcomings of the 1973 AASHTO standard specifications, and these shortcomings were evident. The 72,000 pound or 320 kilonewton AASHTO design truck had roughly half the weight of the maximum truck weight permitted in Ontario, which was 140,000 pounds or 615 kilonewtons. Moreover, the AASHTO and CSA S6 standards did not have commentaries. The procedures for revising AASHTO required support from all 50 states, which would have been challenging to receive. The metric system was being adopted in Canada, but AASHTO had no plans to metricate. The early 1970s also saw the dawn of limit states design in Canada, and the creation of a limit states design code would allow proper calibration to be conducted. And then finally, the ministry was spending $250,000 a year on research and was making significant inroads concerning a new live load model, load factor design, dynamic analysis, and deck design, considering membrane forces. Practitioners were likely to take the advantage of these new findings unless all of these provisions were permitted by a formal design code. So taking advantage of all of these, in November 1975, Dr. Dorton and Paul Chogley of the research branch and Chris Bassi, a lead engineer in the bridge office, proposed creating a new bridge code to the ministry's strategic management committee. The proposal was accepted in principle, and the final proposal and budget were approved in January of 1976. Remarkably, just over 3 years later, the first edition of the Ontario Highway Bridge Design Code was published in 1979. The code development structure was simple. It was headed by a code control committee consisting of 9 members from academia, government, and industry, plus a chair and vice chair. Technical subcommittees were also formed for each of the 17 code sections, with a chair from the ministry or academia, plus typically 5 members. The consultants and university-based participants were paid to ensure, according to Dorton, a sufficient time commitment to meet the schedule. 4 possible categories of content were identified: the code proper, which was prescriptive and legally binding; charts or diagrams in appendices legally binding; a commentary published with the code but not legally binding, and then a supplement of background data of research information published with the code but not legally binding. The first edition of the OHBDC was used to design new bridges owned by the province of Ontario. Practitioners at the time observed that its use increased design time by 30%. The second edition was issued in 1983 and made mandatory for the design and evaluation of all bridges in 1984. The third edition was issued in 1993. And then the first edition of the Canadian Highway Bridge Design Code, which was based on the 93 edition of the OHBDC, with existing bridge evaluation provisions from previous editions of CSA S6, was introduced. The Code Control Committee was chaired by Paul Chogley with Roger Dorton as vice chair. Here I will highlight some of those Code Control Committee members. Chris G. Bassey was an engineer at the MTC Bridge Office. He also chaired the Pre-Stressed Concrete Subcommittee. Barrington Dev Bachelor taught civil engineering at Queen's and chaired the Deck Slab Subcommittee. Jacques Bouchamp was director of the Bridge Engineering for Public Works Canada. Chester Grebsky was an MTC engineer who also chaired the General Features of Design Subcommittee. Roger Green taught civil engineering at Waterloo and chaired the Dynamic Loads and Vibration Subcommittee. DJ Laurie Kennedy taught at the University of Alberta and chaired the Steel Design Subcommittee. Kenneth Kleinbasser was an MTC engineer who chaired the Evaluation of Existing Bridges Subcommittee. Brian Richardson was an MTC engineer who led the Miscellaneous Loads and Movements Subcommittee, and then Ronald A. Temple was member of the Code Control Committee as well. Other technical subcommittee chairs included Leslie Yeager, chair of the Analysis Subcommittee, James Klein, chair of the Substructures and Retaining Wall Subcommittee, John W. Fisher, chair of the Structure Fatigue Subcommittee, William McFarland, chair of the Wood Structure Subcommittee, Alan McCabe, chair of the Construction and Temporary Structures Subcommittee, Waton Lee, chair of the Reinforced Concrete Subcommittee, David C. Manning, chair of the Deck Joints and Bearing Subcommittee, and David McCune, chair of the Accessory Subcommittee. And then we have today with us Bedar Bhatt, chair of the Soil Structure Subcommittee, and Akhilesh Agarwal, chair of the Live Load and Dead Loads and Load Factor Subcommittee. You'll be hearing from Akhilesh and Bedar shortly in this presentation. Some of the technical advances of the 1979 OHBDC include the OHBDC design truck and lane load models, which Akhilesh will be presenting, dynamic load allowance provisions, which Akhilesh will also be presenting, design of the soil shield structures that Bedar will talk about, and then superstructure analysis, particularly lateral distribution of the live load force effects to the main longitudinal elements that Bedar will talk about. And then finally, consistent safety levels through liability-based calibration that Andy will join us later on to discuss and present. In 1984, in a paper, Roger Dorton notes that the cost of developing the code at the time the second edition became mandatory in 1984 was about $1 million. He also estimated that given typical bridge construction expenditure at the time was about $50 million per year, and that the code could have recovered the cost that was being spent in about 2 years and savings in deck rebar alone. He also concludes that perhaps the largest financial benefit, however, is in the area of bridge evaluation, where the new code will enable many bridges to be saved and renovated that would have been replaced at greater expense under the old code provisions. The other major benefit, which is difficult to measure in financial terms, is the provision of bridges of a much more consistent and well-defined safety level, capable of carrying design live loads twice those previously described. That's all for the brief introduction. Our next speaker is Akhilesh Agarwal, who retired from a long career as principal research engineer with the MTO's Research and Development Branch. Akhilesh chaired the Dead and Live Loads and Load Factor Subcommittee, responsible for Section 3 of the 1979 Ontario Highway Bridge Design Code. He subsequently served as the first chair of the Calibration Task Force of the Canadian Highway Bridge Design Code. His expertise in traffic load modeling and bridge evaluation has had a lasting impact on transportation infrastructure across the country. His presentation is on Traffic Considerations for OHBDC, a Historical Account.
Regulatory loads are determined on the basis of capacity of the highway and such infrastructure with appropriate margin of safety to accommodate occasional overloads. Real loads, vehicle loads can be established through province-wide load surveys. Now, the design truck model and lane load and the evaluation loads are developed based on the real loads that goes on the roads. Triple evaluation system addresses three different categories of vehicles and corresponding bridge posting loads. Traffic consideration also go into dynamic load allowance and deflection limits. This is a story of the time when we had no personal computers. The bridges were evaluated and designed using hand calculations with a calculator. Now, in the hand calculations, it's quite difficult to analyze for moving set of point loads, moving set of axle loads, or a moving truck on variety of different bridges. But it's a lot easier to analyze bridges for uniform distributed loads. So in Ontario, vehicle trains were introduced in 1965, but they were not addressed in the ESTO code that was in use in Ontario at that time. So when we were asked what kind of load should be allowed in these vehicle trains, to analyze variety of bridges and a variety of bridge configurations for different variety of truckloads was almost an impossible exercise. So as a first step, we developed uniform distributed load for a group of axles. And the purpose was that we convert a group of axles in a uniform distributed load, which will cause about similar force effect on variety of bridges, and then use that for further analysis. This uniform distributed load was characterized by its length, which was called equivalent base length BM, given by this equation here. For a single axle, the BM would be 0. For dual axle and triple axle, there are these values. In 1971, in the imperial units, Ontario-based formula was developed, which provided the permissible load on a uniform distributed load of length BM. In this equation, the first term is the allowable load in kips on a single axle, which was established by the pavement considerations. The maximum load that was allowed on the trucks was 140 kips for a vehicle train. Now, in this, the BM was in feet and WM was in 1,000 pounds for kips. This Ontario-based formula was introduced into Highway Traffic Act in 1971. It became the province-wide way of controlling vehicle weights. It was not easy to apply at the truck inspection stations. In 1971, a load survey was conducted, and based on this load survey, it was established that there is widespread vehicle overloads in vehicles, and these overloads were found to be up to maximum 22.5 kips, whether it is on the axles or on the gross weight. So that led to a maximum observed load level where the first term was increased by 22.5 tons. This maximum observed load became the basis for development of vehicle models, design models, and evaluation load models for the British Code. It was decided that because the maximum overload was similar on axles and on the gross weight, that the percentage overload on axles was much larger than the gross weight, and that it would be better to have a model at maximum observed load level in order to achieve a uniform live load factor. In 1978, metric system came in Ontario. The pavement engineers agreed to increase the allowable load on single axle to 10 metric tons. Ontario British formula was modified, and assuming that the nature of overload will remain similar after metrication, the maximum observed load level was obtained by adding 10 metric tons to the Ontario British formula. Another survey was conducted in 1975, which further confirmed the maximum observed load level. The survey also indicated that vehicles can be divided into three different categories. Category 1 for single unit vehicles, also known as straight trucks in the industry. and Category 2 tractor trailers or tractor semi-trailers, and Category 3 trains. Earlier bridge evaluations in Ontario were based on ASTO standards, and according to this evaluation process for ASTO standards, the bridges were evaluated and substandard bridges were rated for less than 20 tons, and they were posted for single gross vehicle weight, such as 5 tons, 10 tons, or 15 tons at the bridge site. The truck operator considered these signs to be too restrictive, and they generally ignore. We ourselves have observed some 40-ton trucks crossing a bridge with a 5-ton sign on it. The truck operators also felt that they were just vague warning that the bridge is not capable to carry full load. And some even considered that that was not the gross weight of the vehicle, but the payload on the vehicle. The payload is the amount of load that is put on the empty truck. So there was wide confusion, and the signs were ignored quite frequently. So we decided that bridges need to be evaluated for each vehicle category separately, and that a substandard bridge should be posted for gross weight limit for each vehicle category. For this, we now needed live load models for each vehicle category. Triple posting sign, which you can see today on a lot of bridges, now would look like showing 3 different categories of vehicle and maximum allowable load on each category. It was decided to develop a loading model such that its subconfigurations could be used for evaluation loads. And that led to this OHBD 5-axle truck, in which these axle 2 and 3 represent kind of a dual or triple axle unit. The first 3 axles would represent the category 1 vehicles, and the 4 axles would represent category 2 vehicles, and the full OHBD truck would represent the category 3 vehicles. And the sub-configurations of this OHBD truck are shown on this chart to compare with the metric MOL level. And you can see all the sub-configurations nicely fall around the maximum observed load level. To represent the other miscellaneous traffic, a lane load was developed, and which other miscellaneous traffic was represented by a uniform distributed load. The intensity of this load depended upon the highway class, A with the higher volume classes and B and C with the lower volume classes. For the design convenience, the uniform distributed load was placed on the entire length, and therefore it was overlapping over the truck. To compensate for that, the truck load were reduced to 70% of the OHBD truck axle loads. For evaluation purpose, the Ontario Highway rating trucks for 3 categories were now, as I mentioned earlier, first 3 axle of the OHBD truck made the evaluation level 1 load, 4 axles made evaluation level 2 load, and the full OHBD truck made the evaluation 3 load. They were corresponding lane load, again in similar way as design. Coming to dynamic loads, prior to Ontario Bridge Code, there was general feeling that you don't have any resonance with the vehicle loads on the bridges. But this all changed in 1972, and we were out to test a bridge in St. Jacobs, Ontario. It is in the middle of the town. We went there to do the punching shear test on the bridge. And as we were preparing for the testing, instrumenting bridge and all that, I walked on the walkway on the outside of the truss, just have a look at the truss condition. And when I was around the middle of the span, suddenly the bridge started shaking very badly. And I just could not understand why it was shaking so badly. I looked and there was only a horse buggy on the bridge at that time. So we instrumented the bridge to measure dynamic deflections at mid-span. We measure the dynamic deflection under a heavy truck and under what we found that the dynamic deflection under a weightless horse buggy was almost as large as under a heavy truck. The frequency of the horse's hoof were around 3 hertz. So what we did was we concluded that there was some kind of a causal resonance situation developing between the horse buggy and the bridge. Resonance frequency may be close to the 3 hertz. So we later on selected a number of bridges. And first we got some data from industry. We found that the natural frequency of the springs for trucks is generally from 2.5 to 5 hertz. So we selected a number of bridges which had natural frequencies in the range of 2.5 to 5 hertz and carried out extensive dynamic deflection measurement. And from that, we determined the dynamic load due to those normal traffic. And we found that, generally speaking, the impact value in those bridges were a lot higher than what the IS2 code were providing. A bridge that were outside this range, we found that impact value was quite low. This gave us an idea that in order to avoid high dynamic loads, it's preferable to design new bridges outside the natural frequency range of 2 to 5. But if there are bridges which are between 2 and 5, they should be designed for higher dynamic load allowance. That led to this provision for the Ontario Highway Bridge Design Code, where for frequency and natural frequency bridge less than 1 and more than 6, it is 0.3. For 2.5 to 4.5, the dynamic load allowance 0.45 and gradually reducing to 0.3 on both sides. This became part of the dynamic load allowance in the Ontario Highway Bridge Design Code. Traffic considerations also were considered for deflection limits. The ASTO, they were empirical deflection limits, but we rationalized them on the basis of the human perception of bridge vibrations. People who are traveling in the vehicles, they don't experience any bridge vibration. But people who are walking on the bridge, they feel somewhat less bridge vibration compared to people who would be sitting on the bridge. And this led to 3 different conditions for the deflection limits. For bridges without sidewalks, such as expressways, where you may have only occasional maintenance people on the bridge to experience bridge vibrations. And then the bridges with somewhat less pedestrian use, and then bridges with significant pedestrian use, such as with sidewalks within the town or cities. That led to this chart of all the deflection limits and became part of Ontario Highway Design Code. Subsequently, the dynamic load allowance have been changed in the further editions of Ontario Bridge Design and into CSBDC. Also, the load model for Canadian Hybrid Design Code subsequently have been developed not at the maximum auxiliary load, but at the regulatory load limit for interprovincial transportation, which is commonly known as Council of Ministers loading. Thank you.
Our third speaker is Bedar Bakht, who also retired from a long career as principal research engineer with the MTO's Research and Development branch. Bedar worked extensively with Leslie G. Yeager, chair of the Section 5 Subcommittee on Static Analysis of Bridge Superstructures of the OHBDC First Edition. He subsequently won the Ontario Professional Engineers De-Engineering Medal in 1997. In 2014, he was appointed a member of the Order of Canada for his contributions to civil engineering and cultural enrichment through Urdu and Hindi poetry. Bedar's presentation is titled Bridge Analysis Section of the 1979 OHBDC, A Personal Account.
I would like to relate my experience to the analysis section of the OHPDC through a personal account that I'm going to recount with my friend Aftab Mufti, who is an emeritus professor at the University of Manitoba, now living in BC. I was in England from 1966 to 1973, working with the Ministry of Transportation of UK. And I also did my master's at the Imperial College. I learned that bridge superstructures were analyzed for transverse load distribution by either manual or computer-based methods. The computer-based methods were grillage analogy, finite element method, orthotropic plate method, and the manual methods were distribution coefficient methods developed by Guillaume Massonnet and adopted by Cement and Concrete Association. There were also methods developed by Cousins and Palmer. This is one of the pictures from my thesis in which a 200-pound load is applied eccentrically to a slab bridge, and I have compared the moments given by various manual methods in this slide, but it's not that important. For distribution coefficient methods, the bridge structure is idealized as a rectangular orthotropic plate, and it is characterized by two very important dimensionless parameters, alpha and theta. Alpha relates the torsional rigidities dxy, dyx, d1 and d2 with the flexural rigidities of the bridge, and theta relates the longitudinal flexural rigidity, which is dx, with the transverse flexural rigidity of the bridge along with its aspect ratio, which is half width of the bridge B and the span of the bridge. They are very important characterizing parameters. In this slide, you are looking at the distribution coefficients of an orthotropic plate which has the width of 1 unit, the span of 2 units. You are applying a load eccentrically as shown on the red arrow, and the distribution coefficients go from -1 to nearly 3.4, given by the Cousins and Palmer method, the orthotropic plate analysis, and the design curves of Cement and Concrete Association. The distribution coefficients by all the three methods are very nearly the same. The distribution coefficients by Cement and Concrete Association and Cousins and Palmer were developed for alpha equal to 0. Now, if you remember the equation that I showed, alpha is 0 when the torsional rigidities of the bridge in both longitudinal and transverse directions are 0, and alpha is 1 for slab bridges. Henry and Jaeger will come later, wrote a book in 1958 in which the distribution coefficients were given only for alpha equal to 0, i.e. for torsionless bridges. And I'll explain why that was so. Now, alpha and theta are very useful parameters. If you take two rectangular orthotropic plates, one is twice as wide as the other, but have the same values of alpha and theta, the distribution coefficients across any transverse cross-section will be exactly the same. Now, alpha and theta are very useful in that theta for all bridges in the world goes from nearly 0 to 2.5. Now, alpha goes from nearly 0 to 2. from alpha from nearly 0 to nearly 0.02 has bridges with very little torsional rigidities, and these are timber bridges. Slab and girder bridges have alpha nearly equal to 0.1. Slab bridges have alpha equal to 1, and box girder bridges, in which the torsional rigidity is very large, have alpha between 1.5 and 2. In 1973, I came to Canada and joined the Ministry of Transportation and Communication and found that bridges are analyzed only as beams by a very simple method of analysis. What you do is, if you have a girder bridge, you isolate one girder of the bridge, subject it to 1/2 of the design truck multiplied by S over D, where S is the girder spacing and D for steel girder bridges is 5.5 feet. That was very simple. So it was a huge change for me for analysis of bridges from the complex methods used in the UK and rest of Europe to very simple methods used in Canada and USA. The OHBDC was launched in 1976, and it was the first bridge design code in the world which had a method of analysis. Leslie Yeager of the Henry and Yeager method, he was a professor at McGill University. He was invited to chair this session. Now, I had read Leslie Yeager's book, besides the one I showed you on Cartesian tensors and engineering science and theory of elastic plates, and I was an admirer of his work. In 1976, Leslie Yeager moved from McGill to Acadia University, where he was the vice president, and I met his friend Aftab Mufti, who was the head of computer science at Acadia University. Aftab was not a member of the CHBDC, but he contributed indirectly to the analysis section. The three of us, Les Yeager, Aftab Mufti, and I, did a lot of work on methods of analysis. The ASTRO method of S over D times one line of wheels of a design truck. If you analyze a slab on girder bridge idealized as an orthotropic plate, the transverse distribution of longitudinal moment intensity, which is kilonewton meter per meter, would be as shown in this slide. And it can be shown that parameter D, which had the length of 5.5 feet for ASTRO, is equal to M, which is half the moment due to the two lines of wheels of a truck, divided by maximum intensity of longitudinal moment, mx max. For any bridge, we can calculate the value of D and then use the ASTRO method for analyzing the bridge as a one-dimensional beam. We took, for example, a 4-girder bridge, which had 4 load cases. Analyze this bridge under all 4 load cases, multiplying the weight by the modification factor, which was 0.9 for 2 vehicles, 0.7 for 4 vehicles, calculated the value of mx max for each, calculated the D value for each, and then we used that alpha theta space for plotting the values of D for bridges with different number of lanes. Here you see the values of D for internal girders, internal portions, external portions for 2-lane bridges of basic form. And because we assume the value of maximum moment intensity also depends upon the width of the bridge. So even if the bridge has only 2 lanes, Depending upon the lane width, its width can change. And that change in the width was accounted for by CF. So if you want to analyze a two-lane bridge, you calculate the values of alpha and theta, go to these charts, calculate the value of D for external girders or internal girders, calculate the value of C, read the value of CF from the chart, and your governing value of D, which is D sub D, is simply given by D from the chart 1 plus mu times CF divided by 100, and mu is a factor which tells you how wide the lane are. So now we had a very simple method of analysis, which is as simple as the Astro method with S of 5.5 feet, but far more accurate. I described the bridge in the method in this book, Bridge Analysis Simplified, which was published by McGraw-Hill of New York in 1985. You see, the Henry and Jaeger method that I described before idealizes a bridge not as an orthotropic plate, but as a system of one-dimensional beams interconnected by a continuum. So the method is called a semi-continuum method of analysis. And loads are represented by harmonics. I won't go into the mathematics. You can find it. I will tell you from where. But if you have the first harmonic of any loading, it looks like a half sine curve. And the beauty of that loading is that if you apply that loading to any girder of a bridge, all the other girders receive the same shape of loading. So it's very easy to calculate the distribution coefficient for a loading represented by harmonics. Henry and Jaeger, they had analyzed bridges with zero torsional rigidity, which means for alpha is equal to 0, because in those pre-computer days, it was not feasible to include the torsional rigidities and have a very large number of equations. When Leslie Jaeger met me, the computers had come in vogue, and we revived the semi-continuum method by taking into account the torsional rigidities in both the longitudinal and transverse directions. The method is incorporated in a computer program called CCAN and is detailed in this book, which was also published by McGraw-Hill in 1989. Leslie Jaeger, Aftab Mufti, and I have written 3 major programs. One is CCAN, which is based on the semi-continuum analysis, Plato, which is based on the orthotropic plate method of Cousins and Palma, and ANDICAS, which is for the analysis of cantilever slabs of slab and girder bridges. These 3 programs are in public domain and can be obtained from Simtrack, University of Manitoba. Leslie Gordon Jaeger passed away in 2013. He's the only fellow that I know who has 2 earned doctorates and 2 honorary doctorates. I miss him very much, and we had a very good career doing research together. Thank you very much.
Our fourth speaker is Mike Bartlett, Professor Emeritus of Structural Engineering at Western in the immediate past chair of the CSCE National History Committee. Mike led the initiative to have the Conestoga River Bridge near St. Jacobs designated as a CSCE National Historic Site. The graduate students he has supervised at Western have largely done highway bridge-related research, primarily on the assessment and rehabilitation of existing bridges, and he has won CSCE's Prattley Award 5 times. He will be speaking on the Conestoga River Bridge, a full-scale test specimen still in service.
Good morning. I'd like to start by warmly acknowledging my co-author, Peter King, of Western's Boundary Layer Wind Tunnel. My presentation is basically 5 pieces. We'll start with an introduction and a little bit of background on the need for the bridge. We'll review the design and construction of the bridge and the research conducted using the bridge. And finally, reflect upon the historical significance of the bridge. The Conestoga River Bridge carries Regional Road 85 over the Conestoga River, just east of St. Jacobs, Ontario, which, as you can see from the map, is just north of Kitchener-Waterloo. It has a composite superstructure with 4 slender, variable depth steel girders supporting a cast-in-place post-tension concrete deck. That lower photograph gives you an idea of the slenderness of the structure. We'll talk more about that. The bridge represents the culmination of intensive research activity by the Engineering Research and Development Branch, ERDB, of the Ontario Ministry of Transportation and Communications. According to Roger Dorton, the group was, quote, small but had a surprisingly large number of significant projects underway. Its activities included checking the load-carrying capacities of bridges thought to be deficient using full-scale load testing, carrying out truck weight surveys, Akilish has talked about them already, to develop more accurate truckload models for bridge design and evaluation, and investigating the application of compressive membrane theory to design reinforced concrete deck slabs that require a fraction of the reinforcement needed for conventional designs of the day. Khaled reminded us of Roger Dorton's observation that the cost of developing the OHBDC was saved with the savings of 2 years in deck reinforcement. They recognized that they needed a full-scale test specimen to confirm their findings and also to confirm the dynamic effects of the traffic loads being sensitive to the first flexural frequency of the bridge. Again, Akilish has talked about the buggy crossing the Conestoga River Bridge. And to verify that steel bolts could be used to replace shear studs to achieve fully composite behavior of steel concrete bridge superstructures. Roger Dorton's autobiography celebrates the support received from the ministry's senior bureaucrats. Quote, the senior management became very interested in the Conestoga River Bridge project, and rightly so, as they would be held responsible for the opening for public use of a bridge with many innovations that was not designed to the accepted code. Without this high-level support, Dorton says, this unusual project would never have been realized. They showed a forward-looking acceptance of risk and change, characteristics not always associated by the public with civil servants. The Conestoga River Bridge was selected because it was already listed to be tendered and its rural location limited pedestrian use and, as noted by Akilish, alleviated deflection concerns. They could design a very slender bridge as implied by the elevation view shown and the girder concrete composite cross-section on the bottom. The redesign had several objectives. First, to use a new load model, the proposed Ontario Bridge Design Load, proposed by Chagley and Dorton in 1973, determining the fractions of truckload moments carried by each girder by a computerized grillage analysis that yielded much smaller girder demands compared to those obtained using the AASHTO 1973 specifications. Using distinct dead load factors of 1.1 for the structural steel and the concrete deck, 1.15 for the barrier walls, 1.33 for the asphalt wearing surface, and a very low live load factor of 1.1 because the specified proposed Ontario Bridge design load represented an upper bound vehicle weight. They eliminated any deflection limitation to allow a very shallow and flexible superstructure. It was intended that the first flexural frequency lie outside the range of 2 to 5 hertz. Akilish has told us why that's important, that it's typical of heavy truck frequencies. This would prevent resonance between the truck and the bridge and so markedly reduce the dynamic effect of the live load. They used ASTM A325 bolts as shear connectors instead of conventional welded shear studs. They used a conventional deck slab designed to resist transverse bending by the usual AASHTO 1973 working stress method for the south half of the bridge, but they created 12 test panels at the north half with thicknesses of 180, 190, and 203 millimeters, and transverse steel percentages of 0.95%, which was the AASHTO requirement, 0.6, 0.3, and 0.2%. And finally, they post-tensioned the deck longitudinally to satisfy allowable tensile stress limits at ultimate limit states and ensure composite behavior in the negative moment regions. This photograph shows the steel girders being erected in 1974-75, about 50 years ago. This photograph shows the deck before concrete placement, shows the longitudinal post-tensioning tendons running away from us into the background, and the bolt shear connectors, and the different quantities of transverse reinforcement. So the spacing in the foreground, for example, is twice as large as the spacing in the middle ground. Full-scale load tests were conducted in 1975. Scaffolding beneath the structure, visible on the left-hand side of the bridge, was designed by Peter King and provided access to the instrumentation. This figure shows the static deflections and bending moments due to two trucks placed symmetrically to achieve maximum moment in a side span. The values are shown for each of the four girders of the cross section. The solid lines are the values predicted analytically, and the open circles are the observed values. The agreement between the observed and predicted values is excellent, validating the grillage analysis and so the reduced live load distribution factors assumed for design. These are oscillograph traces. Again, Aklish has shown similar sketches of four dynamic tests where a single vehicle crossed the bridge in the left lane. You can see in that shaded region, the free vibration measured in trace 1 indicates that the first flexural frequency is 1.6 hertz. As this is less than the range of typical truck frequencies, there is no resonance and the dynamic effects are low, as predicted. For the other three traces, the frequencies correspond to the third mode. For the bump test, trace 4, the force frequency of 3.5 hertz lasts less than 2 seconds, but during this interval, the highest dynamic amplitude is observed, 0.25. This figure shows the stress distributions in the girders inferred from the strain gauge readings. In all cases, the observed location of the neutral axis corresponds closely to that computed for the fully composite section and well above that computed for the non-composite section. The bolt shear connectors are clearly effective. The test deck sections performed very well, even though the transverse requirement was as low as approximately 1/5 of that required by the AASHTO 1973 provisions. The Conestoga River Bridge is historically significant because it's novel. It's the only one that we're aware of that was designed using unpublished design standards to be used as a test specimen before being put into regular service. It's also significant because of its creators. The MTO Engineering Structures Research Branch, although small, was carrying out substantial and world-leading research that had a tremendous and lasting impact on bridge design in Canada and, as Chris pointed out, even internationally. Roger Dorton and Paul Chagley, in a 1977 publication to support a CSE national lecture tour about the development of the OHBDC, note, quote, the testing of this bridge in 1975 and an evaluation of the test results has given the required backing to the concepts mentioned so that they have been advocated for inclusion in the code. The Conestoga River Bridge will be a future CSE National Historic Site. Approval's been given. We just haven't erected a plaque there yet. We're now working with the region of Waterloo, who owns the bridge, to obtain their formal support. The wording for the plaque is as shown. Roger A. Dorton, Paul F. Chagley, and others working for the Ontario Ministry of Transportation and Communications Engineering Research Group designed the Conestoga River Bridge in 1974. Their design used innovative criteria developed from recent research. These criteria, validated by instrumenting and testing of the full-scale structure in 1975, addressed the dynamic response of highway bridges, the behavior of concrete deck slabs, and the lateral distribution of truckloads to the main girders. These tests provided the required confirmation so that the new methods could be included in the first edition in 1979 of the Ontario Highway Bridge Design Code, the forerunner of modern Canadian bridge design standards. At one of our planning meetings, Bedar described the Conestoga River Bridge as, quote, the first bridge designed by the Ontario Highway Bridge Design Code. Well, the live load was different, but it's still a nice way to think about it. I'd like to again acknowledge my co-author Peter King, whose MESC thesis at Western is a comprehensive analysis of the Conestoga River Bridge test results, and for Doreen, who puts up with me. That's the end of my presentation.
Bedar Buck will now return to give a second presentation in this webinar. This is particularly appropriate because Bedar chaired the Section 12 Subcommittee on Soil Steel Structures. Bedar was very active with the intelligent sensing of innovative structures NSERC Network of Centers of Excellence and is now adjunct professor of civil engineering at the University of Manitoba. His presentation is titled Soil Steel Structural Design by the 1979 OHBDC, a Historical Perspective.
Soil Steel Structure Design by the 1979 OHBDC, a Historical Perspective. Believe me or not, soil steel structures were introduced in 1886, 150 years ago, by two workers who used to work with metal, and they thought it would be nice to have a corrugated pipe buried under soil. So they made a pipe looking like this. This is a cover that pharmacists use for wrapping bottles. They made the structure and the structure collapsed. Oops, they said, oh, we had the orientation of the corrugations wrong. The corrugation should be circumferential as shown in this slide. And they remade the model and the structure stood. And they had a USA patent in 1986. And since then, tens of thousands of corrugated metal pipes have been constructed worldwide. And these structures were known by different names, corrugated metal pipes, culverts, metal culverts, or whatever. Now, similar to the gut feeling of the conception of the structure, you will be surprised to know that these structures were also designed by gut feelings and not by a rational method. In 1976, when the Ontario Code was introduced, it had a section on soil steel bridges. And I'll tell you about the definition. I was made the chair of that section, and my only claim to expertise of this structure was that I had interpreted the data from an instrumented structure to say what were the moments and actual thrusts. And the real brain of that committee was George Abdul Said, who had studied in 1970 in German language for the original work of Kloppel and Glock. And he was himself conducting research in the field of soil steel bridges at the University of Ontario. The other members of that technical subcommittee are listed here, and really none of them had a very clear idea how this structure should be designed. We had the first meeting of the technical subcommittee, and believe you me, that most of the first day of the meeting was spent in deciding what should we call these structures. So we called them eventually soil steel structures. A soil steel structure, defined it, is comprised of structural steel plates and engineered soil, that's important, designed and constructed to introduce a beneficial action between the two materials, between corrugated metal pipe and the surrounding soil. Now, a bridge, according to the legislation of Ontario and in Canada, should have a span of more than 3 meters. So the small pipes had very small corrugations, and pipes which could be called bridges had 2-inch by 6-inch corrugations. I'll show that to you in a second. Here you can see the 6-inch by or 152 millimeters by 51 millimeter corrugation, where the pitch is 6 inches and the depth of the corrugation is 2 inches or 51 millimeters. Then we decided upon the definitions of the various components of the bridge. The top portion of the conduit wall, which is the corrugated pipe, was called the crown. Shoulder, you can see here. Spring line is the outermost extremities in the horizontal direction. The lowermost point in the conduit incidentally is the hole created by the corrugated pipe. The lower point is called invert, and haunch is the portion shown in the lower left and right corner of the pipe. How does this corrugated pipe hold the load? And I invite you to think of a soup can, remove the lids, and then you can compress it by your fingers very easily, as shown in this slide. This time, you take that can, hold it in your hand and squeeze it so that you apply nearly equal radial pressure around it, and you will find that you won't be able to bend the pipe. I used to have 2 wooden blocks shaped and a soup can without the lids, and used to take it to my presentations, put the lower concrete block down, put the soup can in, put the top concrete block, and let a person stand on the top block. And you can easily see that the very small portion of the can is directly in compression. An analogy can be drawn that the pipe is really in compression, supported by spring supports given by the soil. The stronger the springs, the higher the capacity of the pipe to take thrust. Radial pressure is inversely proportional to the radius of curvature of the pipe. Here you see a very popular shape of a soil steel bridge called the pipe arch. It has a very flat bottom, shoulders of a very small radius of curvature, and the top portion having a radius of curvature in between the two. And you can see that the radial pressure at the haunches is the largest in this pipe. We took a concrete pipe analytically and subjected to the soil load, and there were very large bending moments, as shown in the left side. And then we analyzed this pipe by putting 4 hinges, as shown in the top right-hand sketch, and we found that the bending moments disappeared. Now, the beauty of this small 6-inch by 2-inch corrugation is that it cannot hold too much bending moment. It develops invisible hinges, just like the hinges in this mathematical model. And the result of this forming of those hinges is bending moments disappear from the conduit wall, and the conduit wall is subjected only to radial thrust. Now, the force analysis of soil steel structures obtaining thrust is given by this very simple expression. And TD is the thrust due to dead load. These soil steel bridges come in different shapes. They are round pipes, horizontally elliptical pipes, which are good for vehicles, vertically elliptical pipes, which are good for trains, pipe arches, which are good for water going through the pipe, and pear-shaped pipe, which is the reverse of pipe arch, roughly. Now, the way you calculate the thrust in the conduit wall is you calculate W, the weight of the soil directly above the conduit, and multiply it by AF, which is always greater than 1, and is given in this chart for different shapes of pipes having different ratios of span to rise. So calculation of thrust is now very simple. We had done a lot of tests on actual soil steel bridges under test vehicles and found that you can calculate thrust due to live load by distributing the wheel loads at an angle of 1:1 in the direction of the span of the conduit and 1:2 in the other direction, and simply use this expression to calculate thrust due to live load. So this is the result from one of the tests we conducted at MTO by using their test vehicle. You see, when we apply the live load to the top, the thrust due to live load is mostly limited to the upper portion of the pipe, and the lower portions of the pipe hardly see any effect of live loads. So now strength analysis. So now you have a curved bar subjected to thrust coming from dead load and live load and supported by spring supports, which is provided by backfill. So now suddenly soil, which was just a filling material, becomes an important structural component. The strength analysis, which is the buckling strength of the conduit wall, is indirectly proportional to the radius of curvature of the pipe. If you take soils which are sandy, the modulus of subgrade reaction is high. If you compact the soil very well, it will be as high as 30 MPa. But if you compact it slightly lightly, it will be as low as 6 MPa. On the other hand, if you take clay soils, their model of subgrade reaction is roughly half of that of sandy soils. So the code requires you to have sandy soils as the soils for soil steel bridges. Now in 1988, Akhilesh Agarwal and I conducted a survey of distress in soil steel bridges. Now before I go into distress, I must say that soil steel bridges are much cheaper than conventional bridges, but they are also prone to distress. In this slide, 97 soil steel structures were in distress, and most of these structures were pipe arches. You remember I'd shown you the pipe arch before? And the distress in pipe arches was either in the form of bolt hole tears or in the form of crimping, as shown in the left-hand slide. Now, this is coming because the radial pressure at the haunches is very large in pipe arches. So they tend to bend more. And if you bend that plate, it will either crumple or develop bolt hole tears. To get rid of the bolt hole tears, the bridge code developed a scheme for bolting. And the scheme for bolting it, you always have 2 bolts at a seam. And the scheme is that the bolt nearest to the visible edge should always be in the crest rather than on the valley. You see here the bolt nearest to the visible edge on the valley of the corrugation rather than the crest. Ontario Bridge Design Code has construction provision for only one kind of bridge, and that is soil steel bridges. It tells you how to compact the soil. It tells you that you have the pipe, and then you raise the soil slowly on the two sides of the pipe in layers of about 10 inches, 12 inches thick, compacting them very well, and you can compact a well-graded sandy soil properly. And if you construct that soil steel structure properly, it will have no difficulty. But if you make mistakes in construction, you will have the kind of troubles that we just showed you. The pipe arches, if they are sitting on weak foundations and they have large vertical pressure, the corners will deform. So the later edition of the code are saying that if you have weak soil, then you should have trench on each side of the pipe arch made of either concrete or well compacted granular soil. Here you see a structure pipe arch with concreted haunches, and the structure never gave any trouble. The Canadian Society for Civil Engineering developed a technical committee on soil steel bridges. The chair of that committee was George Abdul Said, and in 1994 that committee wrote a book, Soil Steel Bridges Design and Construction. It has many chapters dealing with various aspects of how to fabricate the shell. You see, the shell is so flimsy that if you reduce it to the size of a soup can, you won't be able to handle it. It will crumble into your hand. So this book, also published by McGraw-Hill, was written by members of that CSCE technical committee. George Abdul Said, I, and Leslie Yeager had the pleasure of editing this book. And all the things that I've talked about are in this book, which was, until recently, was the only textbook on soil steel bridges. The Ontario Bridge Design Code is limited to soil steel bridges made of 6-inch by 2-inch corrugations. After that, the corrugations have become deeper, and because they become deeper, bending moments are now become important. Here you can see a structure of a span of 24 meters. That's mind-boggling, being made by these deeper corrugations. The CHBDC, the code after the Ontario Code, has design provisions for structures made with these deeper corrugations. I would like to thank Professor George Abdul Said for his many contributions to the design and construction of soil steel bridges for the Ontario Bridge Design Code as well as the Canadian Highway Bridge Design Code. George has retired from University of Windsor and lives in Florida. And that concludes my presentation. Thank you.
Our last presentation is by Andrew Nowak, Brassfield and Gorey Professor of Structural at Auburn University. Andy worked with Nils C. Lind of University of Waterloo to carry out the calibration of the factored load combinations and resistance factors in the 1979 OHVDC. He has subsequently been widely celebrated, recently winning the American Concrete Institute's Charles S. Whitney Medal and the Mette A. Souzen Award for Excellence in Structural Research. Andy's presentation is titled Calibration of Limit State Design Provisions for the First Edition of the OHVDC.
I will talk about the history and some important implications of calibration of Ontario Highway Bridge Design Code and that procedure was then used for the calibration of AASHTO code, Canadian Highway Bridge Design Code and AASHTO code. The procedure included selection of representative structures, selection of limit states for consideration. It was not covering all the limit states at that time. Very important was development of a reliability procedure for that calibration. Development, selection, verification of statistical parameters of load and resistance. Also, something which has not been done before, a lot of this was a pioneering work, was target reliability index, how to select this, what are the criteria, and eventually load and resistance factors. The representative bridges were selected by the Ontario Ministry of Transportation, and the engineers from the ministry provided us with a large number of structures trying to have variety, but in the same time being realistic as to how many different structures we could consider. So we considered the following categories: non-composite steel girders, composite steel girders, pre-tensioned concrete girders, and post-tensioned concrete decks. So this was these four types. We looked at the reliability, and that was also a first time where the codes were actually looked from the probability point of view. If we have load carrying capacity, resistance, represented by a certain distribution function, and load represented also by another distribution, resistance in blue and load effect in red, then the difference between resistance and the load represented the safety margin, which is shown here also as a random variable represented by green color. We are interested in what's the probability that the margin difference between resistance and load is less than zero. So probability of failure. The actual values of probability of failure are very small, 10 to minus 5, 10 to minus 6, or even less. Therefore, the actual size of that area would be so small that I wouldn't be able to show it. It is within the thickness of that green line. If we look at the three-dimensional case, and that's how we were trying to develop the procedure to actually calculate the load and the resistance factors. When we have these three-dimensional case relationship between the load and resistance, and consider that hill, which represents the variation for different points in the space of load and resistance, if we consider line at 45 degrees, then if we would cut off along that line, the part of that hill, what we cut off, the volume of it is equal to probability of failure. We are interested, of course, on having that volume as small as is required. That's number one. But we are also interested in knowing what would be the most likely value of resistance and most likely value of the load if the structure is to fail. And that point is in the theory of reliability of structures, we refer to it as design point. So we had to calculate that volume of what we cut off and what are the parameters of the design point. So we were to formulate limit state functions. The simplest form of a limit state function is G equals resistance minus the load. If we make it equal to 0, R and Q are random variables, then we have G, which represents a straight line. The safety margin can be also considered as the ratio of resistance divided by the load. And as long as it is larger than 1, or equal 1, then it's okay. If it's less than 1, it's not good. And the same with the first equation. If G is negative, that is a failure. Now, in our case, in Ontario Highway Bridge Design Code, we were considering a load which had several components. We considered dead load, of factory-made precast steel components, which was assumed that the accuracy of determining is quite high. And then we considered another component of dead load, which represented reinforced concrete cast in place components. And the third one was the wearing surface, typically asphalt or some other wearing surface, which is subject to uncertainties because of additional layers added during the operation of the bridge. In addition, of course, the very important one is the live load, and important was the dynamic load, which we add to live load. And in cases where applicable, we may have some effect of pre-stressing, especially a secondary pre-stress load. So that was the load. Then with this representation of the load, the reliability index can be shown, and we used both forms. One was if we use the equation that R over Q equals 1, then the reliability index is as shown above. That means logarithm of the mean value of resistance divided by mean value of the load, divided by the coefficient of variation of resistance squared plus coefficient of variation load squared. If the limit state function was linear R minus Q, then the reliability index can be calculated using the formula which is shown below, the mean resistance minus mean load and standard deviation of resistance plus standard deviation of load to the second power. These equations, from the theoretical point of view, are absolutely perfect. The first one, if both R and Q are log normally distributed, and the second equation is perfectly correct if both variables are normally distributed, so log normal or normal distribution. When they are not normal, when they are not log normal, then the formulas provide only approximate value. Statistical parameters. A lot of these values were simply not available at that time. Today we have them, but in development of Ontario Highway Bridge Design Code, we were really exploring the virgin area. The parameters which describe from the statistical point of view each of the random variable, the most important ones are the mean value, standard deviation, but we would prefer a non-dimensional parameter such as bias factor. And the bias factor is the ratio of mean to nominal, mean divided by nominal, and coefficient of variation, which is the ratio of standard deviation divided by the mean. So for dead load, for the weight of factory-made components, bias factor assumed is 103 and coefficient of variation 0.04. For cast-in-place concrete, bias factor 105. And coefficient of variation 0.08. And the wearing surface, we assume that the bias factor is 1.1, coefficient of variation 20%, 0.2. Why I'm reading these numbers, this is very important. Why is it important? Because Ontario Highway Bridge Design Code development actually first time named these values, and after that, all those who are doing the reliability analysis of bridges were just following these numbers. They were taking these numbers and referring to Ontario Highway Bridge Design Code. And the interesting thing was that these numbers were actually provided by Ministry of Transportation engineers who did some analysis, and they gave us these numbers to use. Live load, that was, and again, for the first time, there was serious statistical analysis done, and it was based on the truck survey in 1975. The number of trucks studied was a little bit over 9,000, and having these, we calculated cumulative distribution functions for gross vehicle weight, but gross vehicle weight was not as important as load effects. So we were interested in moments and shear forces. And this we calculated using influence lines. We ran these 9,000 vehicles from the survey. The survey was done over the period of 2 weeks by police agents who would stop vehicles on the highway if they seem to be heavily loaded, and would, using the manual methods, using the portable scales, they actually did the measurements of what the actual weights were. So the measurements were accurate, but of course 9,000 is compared to the number of traffic was relatively small number. There was a question, what live load should we consider? Should we consider annual maximum live load or 5-year maximum or 10-year? It was agreed to consider 50-year maximum live load. So our survey was done within a period of 2 weeks. And there was a question, how are we going to extrapolate this result to represent 50-year mean maximum? How about getting the coefficient of variation for the maximum value for 50 years? That required some statistical extrapolation methods. We did this, and again, these considerations involved a number of researchers and led to first-time developments of these numbers. It was assumed that the bias factor ratio of mean to nominal is 1.15 and coefficient of variation is 12%. That was supplemented by variation of dynamic load. So the actual value, which was live load and dynamic load, we ended up with the coefficient of variation about 20%. Dynamic load went through a number of cycles in the code. The first, not yet the final code, but in consideration of the code, there was first considerations to relate dynamic load factor to the dynamic properties of the bridge, the frequency of vibration, and so on. And it went through a number of cycles. At one point, it was 45% of live load, but then especially later when dynamic measurements were corrected, it went down to 10 to 20%, depending whether there is a single vehicle or two vehicles side by side. The coefficient of variation was agreed to assume 80%. Resistance was basically considered by using the test results which were available at that time, some at University of Minnesota, some of the Canadian data, some from Lehigh University. The consideration was for the material, consideration was for geometry, the dimensions, and the model, uncertainty in the model representing resistance. So we considered a number of limit state, positive moment, in tension, the positive moment in compression, the negative moment shear force, and permanent deflection as the service limit state. For resistance, post-tension girders, many of these numbers are still used, but a number of them have been verified and changed based on the new data. The bias factors, as you can see here, for ultimate limit state, for service limit state, and the coefficients of variation are given as percentages here. The comparison of the calculated reliability indices as a function of the ratio of nominal resistance divided by nominal load. That is the traditional safety factor. Yes, nominal resistance, nominal load. If you divide them, the old allowable stress design was based on that consideration. So we calculated the reliability indices and plotted them. And by consideration of that wide spectrum of reliability indices, it was decided to use the target value of 3.5. It's interesting that this 3.5 survived many other attempts, considerations, and today target reliability index for girders, even in ACI for buildings, is 3.5 for steel and concrete. So that 3.5 is being a historical value is still in service. There were various considerations, and that was, as I mentioned, used in the Canadian Highway Bridge Design Code, and in AASHTO it was also taken. There was more concern about service limit states, especially for pre-stressed concrete. In the calibration, it was taken as 1. Today, in some newer studies, for some service limit states, it is as low as 0. A very meaningful presentation of results. Reliability indices calculated for existing bridges which were provided by the Ministry of Transportation. We calculated using the nominal values as available from the technical drawings and other sources of information. We calculated what these reliabilities are, and then we calculated what would these bridges be if they were designed by Ontario Highway Bridge Design Code, if they were redesigned, what would be the value of resistance and load? And consequently, what would be reliability index for existing structures using the statistical parameters which I presented earlier, and calculated reliability indices if the same bridge was designed to satisfy the requirements of the new Ontario Highway Bridge Design Code. And if you look at this graph, it really well summarizes the advantage of the new code. There is a wide spread of reliability indices from smaller than 2 all the way to 12 or 14, while the new design provisions provide a very narrow scope of reliability indices. Since the time of Ontario Highway Bridge Design Code, we had quite a number of changes. We have new, more statistical data. We have new material data. We have much better analytical methods. The reliability analysis procedures are changed. So all these can provide some improvements. I would stress that Ontario Highway Bridge Design Code, as a pioneering program, made a great contributions because it served as a basis for a number of major other codes, not to mention Canadian Highway Bridge Design Code, but AASHTO. AASHTO LRFD code is very much based on the, in particular, statistical parameters of load and resistance that was based to a large extent on Ontario code. I would like to finish with the acknowledgements. Ontario Ministry of Transportation did a great job by taking on the projects. I would like to thank Roger Dorton, Paul Chagoli, Bader Bakht, Hit Gruni, Akhilesh Agarwal, Bala Tharmabala, and others with whom I had honor to work with, and University of Waterloo at that time when I started the work there, and I collaborated with Niels Lind and Roger Dorton. Thank you very much.
The first thing that's come through is just a thank you. So this was great. Look back at some of Ontario's bridge history. Thank you so much for speaking today. Is our first.
Thank you very much for inviting us. And thanks for all my colleagues. Nice meeting you all after a long time.
I'll start us off with our first question here. What is the opinion of the OHBDC authors on the volunteer-based process for development and maintenance of the present-day CHBDC through CSA?
Sure, I'll take a jump at that. I think it's fair to say that it's a little patchy. There are some volunteer code committees that are very efficient, and there are other volunteer code committees that are a little harder to make work. Though I have to say the 2025 edition of the OHBDC was targeted to be published in 2025 and achieved that target. And I was involved with the concrete section primarily, and there were an awful lot of revisions and improvements to the concrete section. So I don't know, it's what we have, and it seems to work. Thanks.
What was my opinion on this is that significant amount of work was done for the first edition of CHBDC, and significant amount of modifications have been done for subsequent editions. But from now on, further revisions and additions are comparatively small and minor. So volunteer-based process will still work quite well.
Thank you very much. I'll move us on to our next question here. I looked at a bridge from around the 1940s. It was designed for two 20-ton trucks. It was still carrying CL 62.5 loads today. How big is the margin for old designs?
A long time ago, I did a comparison of bridges that were designed using allowable stress design standards AASHTO and the AASHTO HS20 loading, and compared them with modern loading and modern design requirements. And particularly, it depends a lot on the dead to live load ratios that you're looking at. So the first edition of the OHBDC used to say if you're evaluating a truss, check the floor system before you check the main members, because that's probably where the problems will occur. And it's true that the floor systems tend to be less appropriate for modern loads than the main structural elements. But I'm not surprised to be reading this comment, in the sense that there are lots of bridges that have been around for a long time that are still happily carrying loads.
My comment on this would be that the earlier design standard were based on working stress, and working stress design had significantly larger margin of safety. And that margin of safety, fortunately, has been able to allow us to carry heavier load on the same bridges. But now with greater understanding and better understanding of the margin of safety and improved design standards, we are able to explain why those bridges are still able to carry that load. But it's mainly because we had much larger margin of safety in the working state design compared to the limited state design.
Thank you very much. We'll move on to our next question. Do you think current government and MTO are doing enough to match the level of R&D we were doing before the 2000s?
Well, that is something probably none of us are in a position to answer, because the research R&D was eliminated at the time when I retired, and the structural R&D was moved as a small group within the bridge office. We don't have anybody representing bridge office here today, but they would be the only people who would be able to answer this question properly.
Thank you very much. We'll move on to our next one here. What are your most recommended books for bridge engineers?
If you haven't read Roger Dorton's autobiography, I would put that right at the top of the list. It covers a remarkable career, 60 years in private consulting and in government work, and it's an inspirational thing to read, in my view.
The number of books that Bedar Bakht have written, I think they will be quite useful for bridge engineers.
Thank you very much. As a pioneer of the code, do you have any advice to current participants of technical committee members?
My advice would be, don't be afraid of putting in new ideas and pursuing those ideas. Only then you can have a real improvements in the technology.
I'm not sure if I qualify as a pioneer of the code, but one of the things that I've noticed, not so much perhaps with the bridge code, is that often changes are made to standards and the reasons for the change get lost. And so really working hard to document reasons for changes so that going forward, future committee members understand those reasons. People like Akalish have always been very valuable on code committees because they have long memories and they can remember a meeting that took place 20 years ago where a decision was made and make sure that rationale is present when that decision is being reviewed.
All right, thank you very much. It's inspiring to hear from legends of the Ontario bridge engineering community. Wishing you all well. Thank you for your important and inspiring work. So that one's a bit more of a comment, but just a big thank you.
Thank you very
And
much
our next,
for this opportunity. It was a real pleasure.
we have two last questions here. Where do the speakers see Ontario's bridge codes heading in the future? Any specific areas you think are deserving of updates?
Well, as we all know, the Ontario Bridge Code already have been absorbed and in the Canadian Highway Bridge Design Code, which is supported by all the provinces in Canada, and it's an excellent document.
Going forward, I think the big thing that's on the horizon, it's here now, is structural health monitoring. And currently the evaluation provisions in the CHBDC don't really address structural health monitoring, and I think that would be an important addition. Particularly major bridges are now being constructed with all kinds of sensors to be able to be monitored, and we need to think about how we're going to verify and use that information.
Thank you very much. Please describe how you studied dynamic load allowance and bridge crossing speed. Did you consider how heaviest trucks have many axles versus lighter trucks?
Yes, these have been considered. Heaviest trucks would have a heavier load, but somewhat lower dynamic load compared to lighter trucks. Also, if you have more axles in the truck, all the axles are not in harmony. They do not provide the maximum dynamic load simultaneously. But those effects are taken into account already when we measure the impact under normal traffic, where we have variety of trucks with some heavy load, some lighter load. So all that comes within the dynamic testing of a bridge. Eventually, in a large number of measurements on a bridge under normal traffic, you pick up the sort of distribution of dynamic load allowance, and that would provide you the maximum and as well as mean and all that necessary for calibration of dynamic load allowance.
Okay, I would like to respond to it. To several questions raised before, one thing is, don't be afraid of putting new ideas which look almost absurd. And I did something like that absurd idea. I and a few colleagues of mine, very senior colleagues, wrote a paper that the dynamic load allowance should be got rid of, especially for the evaluation of existing bridges. And the reason for that is that if you remember the curves that Mike and Akhilesh had shown, the dynamic increment takes place over a very small period. So the rate of change of strain is very, very high. And if you remember your strength of materials, when you test a material at a very high strain rate, its strength goes off by an order of magnitude. So we have used that argument to say that dynamic load allowance is not valid, especially for evaluation of existing bridges. And I also support what Mike has said, that especially for evaluation of existing bridges, structural health monitoring should be a factor. In our code, there is a factor which relates to the inspection level. That if the inspection level is very high, you have that factor larger. But if you inspect the bridge by structural health monitoring, you can increase that factor even further and get more juice out of existing stock of bridges. Thank you.
Thank you very much. We have 2 questions left here. I'd like to take a look at this one and then we'll finish off on the other. Do you see a need for doing a new truck weight survey? And if so, what types of trucks should we focus on in terms of gathering data?
I think we should now do vehicle surveys by weighing in motion. They're much cheaper and more reliable. And the province of Manitoba has several bridges which are instrumented for weighing in motion. So vehicle weight surveys by stopping trucks and weighing them is an outdated thing. I think now we should go to weighing in motion, which has become an established science.
Trucks in Ontario have had historically very serious problem with the airlift axles. And in the beginning of this century, certain regulations were put in place to discourage use of airlift axles or change them to self-steering axles. But these were implemented in the industry gradually on different type of trucks at different time. So it's necessary to see how those regulations are effectively working. And for that reason, at least in Ontario, it is necessary to carry out these truck surveys periodically and then evaluate if the airlift axle problem have been resolved. If not, we still have serious problem within Ontario.
Yeah, the only thing I'll add here is that first, we really do need to do more surveys because I don't think we've got a very good handle on the weight distributions of traffic on the road right now. The surveys that have been done recently have been ineffective because they haven't been able to uncouple permit trucks that are allowed to be overloaded because they're traveling on a permit with normal unpermitted traffic. And if you can't separate those two, then you don't really know what you're looking at the upper end of the weight distribution histograms. And so, yes, we need to do it, and we need to be more rigorous about trying to control for permit trucks.
1975 survey, which I coordinated on the overall in the province, that was not done using portable scales, but it was done at all of the truck inspection stations using their fixed scales. The team actually traveled to each of the 50 stations at that time and collected data randomly on the traffic. The permit vehicles were not so much included in that survey.
Thank you very much. All right, we'll finish off on this question. Looking back, can you tell us about an example of a bridge you remember working on and what made it memorable?
It's a very good question. There were several bridges which would be memorable. I would say most memorable example for my case was that St. Jacob's Conestoga River Bridge, Truss Bridge, where we experienced quasi-resonant vibration of the truss by a very comparatively weightless horse carriage. And that's what led to our feeling that there may be potentially a quasi-resonant vibration under trucks. Further data collection and studies confirmed that yes, it is. The truck suspensions usually had frequency from 2.5 to 5, and within that range we found that bridges which had natural frequency in that range 2.5 to 5 exhibited much higher dynamic response, which confirmed what we observed on the Conestoga River Bridge at St. Jacobs.
I have a different story. Many years ago, I was working for Buckland and Taylor, and we had a job evaluating bridges on the ore haul route between a mine in Faro, Yukon, and a port at Skagway, Alaska. And I was working on the Carmacks River Bridge, which is a 250-foot through truss span constructed in the 1950s. Very slender compression members because the S6 code of 1952 was actually quite unsafe for these compression members. But I remember being on a ladder truck on this bridge at 2 lanes. They closed 1 lane. Traffic was using the other lane. I was up on this ladder truck trying to check member sizes and things, and the vibration of the trucks crossing the bridge was exciting the suspension system of the ladder truck that I was on, and it was terrifying. So we think about trucks exciting bridges, but in this case, it was the bridge that was exciting the truck that I was on. That was quite lively.
All right. Thank you all very much for your participation. Thank you to Chris Marmigas, Khalid Bakhtash, Dr. Akalesh Agarwal, Dr. Bader Bakht, Dr. Mike Bartlett, and Dr.